Hi guys, how are you? I hope you are well. Alive. Today we managed to do it. Today actually managed to go live. So worry not, we are going to make it. Today we are going to make sure that we build that amazing app that we have been always dreaming to build. You can invite your friends, they can join. We can enjoy together. We can learn together about AI, about how to make great AI tools, about how to actually work on deployments, working on designing AI models, what it takes, how much data do we need to build one, how much capacity do we need to build one, and how much skill do we need actually to build one. If you have joined, you can say hi on the chat. You can say hi. Where are you watching from? You can just say hi on the chat. You can like the live. We can learn together, guys. Yeah. So we are going to start in a few. Let's see. Uh, just waiting for few people to say hi, and then we start. Then we start the live, guys. Just waiting for someone to say hi. Are you ready? Are you ready? And then we do it. Yeah, if you are ready, today we are more than stable. We have more than stable internet. All right. Okay, let me just go straight into exactly what we are building. There we go. Yeah, Daylight Plus. South Africa. Huh, how is South Africa? How is everything there? So let's just go straight into this thing. This one is going to be easy, extremely easy on us. Extremely easy, very simple. So what exactly are we going to be building? We want to build a large language model. In short, that is AI that we are going to be building. So it's going to be very simple project, very simple demo. But before we go to the demo, there we go. So we can just look at some few things that we are going to be building today. What exactly are we building? Very simple stuff. We are going to build a large language model that has some few things that we need to do. We need to understand what is a large language model? What is the architecture? How do we build a clean architecture for a large language model? Exactly, that's what we are going to be doing. But what are some of the requirements that we need to have as we build a large language model? We need to understand things like parameters. What do these people talk about when they talk about parameters like 10 billion parameters, 10 million parameters? What capacity? Why do they need GPUs? Why do they need these large CPUs? All those things we are going to know why and how we can actually tackle all these things in an easy way. So we are first going to go through the overview, then we are going to get into the actual stuff, the building stuff. So basically, we need 10 million parameters. of data. And what do we mean by the word parameters? We are going to figure out, we are going to see out. So first of all, we are going to build large language model where you can basically write your own chart, then it gives you response based on the data that you have. Ours, we are going to train it mostly based on text. So where are we going to really get 10 million parameters, or how do we get about that? First of all, in case you think it's complicated, you don't need a complicated hardware. For example, I'm going to design it with my own machine. My own machine only has 8 GB of RAM. You only have 8 GB of RAM. That's all we need. And a good capacity, 500 space, GB of space, that's not big. That's a common standard. 250, that's a common standard that we can have. Very easy, very simple stuff. So we only need hardware, just a simple laptop. How long does it take for us to build or to train this model with 10 million parameters? Very easy, very easy. Like 30 minutes to 4 hours. The actual training process. For example, you have heard about GPT. It takes like 4-6 months to train a model. For us to see 3 months, like months to train a model for us to see, or for us, the end users, to use it. That's not complicated. That's very easy. That's very easy. So you are going to see where does it come to play that you need all this much time for us to build a model like that. So we are going to see. So what do we need? What do we need? There are things that are called weights. I know you people have heard about people talking about open weight, the weight of the model. We are going to see all that. Whenever we are going to get into the code, we are going to see what is the weight of our own model. We only need 10 million parameters of data. Nothing big, nothing huge, nothing huge. So for example, we are going to need 10 million parameters. We are going to build an AI layer with 6 transformer blocks. We are going to see what are transformer blocks. After that, we are going to build something with a very standard context of 256 tokens. Some context, we are going to see what is a context. So after that, we are going to know where do we get data, where do we source our information from, where do we get, or where do we source actual data, sourcing of data. For example, you don't need complicated stuff or complicated data to train your model. For example, I can train a good AI that knows how to write a poem. But how do I train it such that it is very good in writing poems? Very simple. We feed it with data that has a lot of poems. So our AI will only understand in that context. For example, what is a context? In case you are wondering what is a context, you have been trained only to speak in your local language. So that means it's very hard for you to speak a foreign language. Why? Because you have only been trained to speak on that specific language. That's exactly what happens into AI. You feed it with a certain type of data, so that means it's only going to think inside that scope or inside that kind of context. So that's what we call context. And that's where we need to know, or we need to target, how do we need our AI to look like, depending with the kind of data that basically we have. Then there's another thing that we are going to learn later. We are going to figure out, that is teaching the machine to read characters via tokenization. We are going to understand what is tokenization. For example, let's debug what is tokenization. Before you start training AI, you need to do something called translating that raw text into mathematical language. For example, when we have hello world, you can transform hello world from that simple hello into mathematical, into integers, basically into integers. So each word you assign it to a certain integer. So basically this one we call it converting strings into integers. We call it story. You have heard about the word story. Integers, converting string into integers, and vice versa. So that's how we are going to do that. So basically, it's encoding into machine language. So what do we mean by the word machine language? It's very easy. Machine language is machine speak in bytes, in numbers, zeros and ones. So this is what happens. When you type hello world, like the word hello, then it transforms that into zeros and ones. Now, once it transforms that into zeros and ones, then it, it interprets that. Then the moment that you want to get a response, it takes the zeros and ones and then it decodes into now the language that you want to speak or the output that is trying to basically get. Very easy. So with that, we are going to see how we do that tokenization and converting from strings into integers for our machines to really understand, to really learn all this. So another thing that we need to really know is finding things we call engine with shifted context windows. We are going to see what is a context window whenever we are trying to write the code. So there's these things that we have called context. Context. We are going to see how we build context, how our machine build their own context. For example, there is a term that we can use that is called self-attention. Self-attention. What is a self-attention? Self-attention in models is basically this one. These are models that decide which past tokens matters right now. For example, whenever I'm asking question, hello, so I expect the machine to understand that and give me output. So it will go inside the zeros and ones and then it interprets. Now, what matters most whenever I'm giving out the output or I'm giving out the basically the output? We are going to understand all things: parallel attention, what do we mean by parallel attention, mode held attention, feedback rewards, all those kind of stuff. Then after we understand bits and bits and bits of everything, we are going to later now assemble the complete system, assembling of the 6-layer transformer blocks system. That then we make sure that now we stack them together and then we get an output. So basically building AI, it's step by step. You need to collect the data, build layers and layers and layers, train the AI so that you come up with a complete working model. So it's not that complicated, it's not that hard as we might think. It's not that hard as we might think. And then later, we are going to basically deploy our AI, and we are going to see where we deploy our AI and how we can later add things like UI now where people can interact with your AI. But in case you don't want to do that, you can open source the AI model and then it can give people whatever they really want. Now later, after now we have the 10 million parameter simple GPT, very simple words. Then we can later do what? We can later, as simple as now, keep expanding with the data that we have. As long as we have the architecture, then now we can collect more data and keep training our AI and keep training our AI. So we can just go straight to the build. Enough of that. Enough of wording. We can go straight into building this awesome system. So where do we start? Where do we start? Very simple. Very simple. Let me just go and create. I need to create a folder. The 11 YouTube. Then I'm going to open this and use our editor of choice, our favorite editor. We can use our favorite editor right here. I'm going to give you the steps in case you want to get the repo, the pre-built system. You can check on the description. We already have the repo or the repository link with all the guidance that we need to build our AI system that we need to build with our AI system. And actually, the structure of how we are going to basically build it. Not that hard. So you can check on the description. Then you're going to get the repo. It's public. Once you are there, you can give me a star. You can start the repo. You can give me a star of that repo. So in case you want to get it, let me GitHub. You can check here, we have the repo. You can clone it. And you can see everything, including our file structure, how exactly it's going to look like. So you can just go ahead and just clone that repo. You can access that repo. So basically simple. I want us to build the file structure first of all. First of all, we need to build our file structure. Then we are going to explain what happens and what folders do we need. Why do we need this kind of structure right here? Very simple. First of all, we are going to create a folder, data that is going to house all the data that we are going to use for training. Then over here, we are going to now design the AI right here. But apart from that, we need things like our chat interface, where we are going to write the chat interface right there. We also need files like, let's write a configuration file that we are going to explain why we need the configuration file. What else do I need? I need the train.py file. I need the training.py file. And I also need the chat, requirements.txt. We need the requirements file, that is requirements.txt, text file. TXT means text file. It's a text file, basically text file. Yeah, there we go. So in our requirements.txt file, these are the files that we need for now. But before that, because we are using Python, we need to have a virtual environment. We need to have a virtual environment where everything is really going to run at. So I'm just going to open my terminal and create my my environment. Python, yeah, basically Python. Let's see, we are going to create an environment file. So it's basically creating. There we go. It has created. Now we need to then script activate our virtual environment, and there we go. So here, most of the commands that we are going to run inside our virtual environment. But for now, we need dependencies that we are going to use to train our AI. So the kind of dependencies that we need basically are the packages that we need. We are going to explain each package and why we need it. First of all, we need PyTorch. We need PyTorch, that is torch. We need torch, it should be a bigger version 2.5, 2.0. Let's use version 2.0. We need NumPy. Remember that we are working with numbers. We need NumPy. Let me zoom this. I think this one is disturbing. Let me first of all switch off this extension. I need to switch off this extension, right? Okay, let me minimize this. I want to switch off this extension. It's annoying. Not Xcali draw. Am I forgetting the name of my own extension? Anyway, we are going to just work with it like that. Control-Shift-P extensions. Extensions. Check extensions updates. No, it's fine. It's fine. We can work with it just like that. We need extensions like environments like that one. TikTok and not TikTok. Yeah, TikToken. We need TikToken. We need TQDM. We're going to explain. Then we need requests, of course. We need requests. I don't know why I'm forgetting. I want to switch off this extension. It's not. It's really annoying. Yeah, power mode, sorry. Yeah, it's annoying. It's going to switch off right now. This power mode extension, enable. Is switch off settings, enable to activate, enabled. That one should work now. There you go. It's not annoying anymore. So after we do the requirements.txt, now we need to install the requirements.txt. Very simple. How do we install the requirements.txt? We're just going to run pip install requirements.txt. So inside here, we are going to run pip install install requirements.txt. There you go. So let's install all the necessary dependencies right now. So as we install all these dependencies, I think we already have everything that we need by now. What's remaining now is writing the actual code. It's writing the actual code. So we are going to go straight into the configuration.py so that we set up our normal configuration that we need here. In our configuration.py, we need to import several things. Remember the torch that we imported? Import torch. We're going to import torch. Then we are going to create a function that is going to get device. So what extension is it going to get device here? So first of all, in our torch is going to our CPU. It's going to basically understand the system that we are really using for it. Whenever it's running the processes, it can understand, yes, I need to run this process smoothly right here. So we are going to check if CUDA is available. Then we are going to return CUDA right here. So I think we can just return CUDA like this instead of writing that buggy code. We can return CUDA. What if we don't need to check this? We need to check torch, not elif. Don't need to search for torch. We need to check if it has attributes. It has attributes. And basically this is going to do several things as we explain this code up to Z. There you go. So we are going to check the kind of chips that we are still using, and if and also check for torch.backends, the kind of MPs that we are using. And then if it's okay, we can return the MPs. Basically, it's trying to configure the kind of system we are using. So if it finds that we have good systems, or our hardware is compatible with the kind of task that it's trying to do, then it's going to use that. So basically we can return the device here. We can assign the device and then we return this function as the device. We can call this function right here. But we can create we really need to print out. We don't need to print out the kind of machine that we are really using. So basically, we have told it, make sure that you use the correct device right here. So this PyTorch here is first going to understand our machine. So it's going to check our machine and then use the CUDA library to see the kind of machine that that we have. Interact with our hardware and know what kind of machine that we have. So basically, that's the first setup that we need to do. So apart from that, we are going to do some few things right here. We are going to prepare extra files because we already have these files. Let me see, what first do we need to prepare? Do we need to prepare the data? Not really. Not really at this moment. We don't need to prepare the data first. Let me see, do we have any file in the data? No. So we don't need to prepare the data. We can prepare the input of the data. We can prepare things like the model. We can design the model. Let me see. Yeah, we need to design the model first. We need to design the model first. Let me see. Anyway, we can reference from this document here. We can reference from this document that we created last time. So after we configure our machine, then we can get the training data. So we can just basically go straight to the data and first of all download the data. Download.py. We can download the data.py. So in downloading the data, what do we need? We need to scrap from the source of data that we have. And for our case, we are going to use specific data that is called the Shakespeare data. So the Shakespeare data is, we are going to basically scrap that data and see what that data has. So it's very simple. So if you copy this link, and let me see, let me first of all format this link. So if you follow this link, you can clearly see that this is just raw data of Shakespeare writings here. It's a lot of data. It's very simple data. And you can see I sent this through rivers and bold, basically poems, writings here. It's a lot of data that you can check from Shakespeare. It's a good amount of data that you can check. So basically we are going to use this data and train our model to write also a poem, to basically write a poem. Very simple, very simple. So in downloading the data, we need to do several things, first of all. So in downloading the data, we don't need this. So basically we can import, we need to import the OS library, and also we need to import requests. Why do we need to import requests? We need to import requests so that it can fetch the data. The request basically acts as fetch. Just go online, fetch the data, then give us the data. Basically simple, give us the data. So we can define dataset URL, in which we are going to assign the dataset URL as this URL right here. So let me just copy the URL with this data. And then replace this URL with this data. Yeah, there you go. So we have the dataset URL, in which it's that dataset URL. We need to close this into a bracket. Oops. Yeah, there you go. We need to close that with the URL, and also we can define the output. And the output will be where we need our data to go to. Basically, it should go to the folders of data. See this data. Just go inside this folder of data. Then create this one as the input text. Input.txt. Input.txt. So basically what we are trying to say is, the moment that you fetch that data from this, from basically here, just dump it inside our input.txt file. So it just does or dumps the data right there. So after we dump the data right there, now we can define the function to download the data. So how do we can define download we can just define download. We can define the download, we can pass the URL, and inside the URL, I don't want to use the autocomplete. We can convert our data into a string in which we are going to assign it to the data. We are going to assign it into dataset underscore URL. Remember this dataset right here? We are going to assign it right here. Okay, that we have assigned to string. Then comma, we are going to pass the data set. You are going to pass the data set and also convert that into a string. Oops. We are going to assign that, or we are going to change that into a string. Then we pass that into the output underscore dir into the output directory, in which this one should point to none for now. In which this one can point to none, and it should look like this, yeah. Full colon, because this is basically a function. Let me just close this window here. The download dataset, this one looks clean. I can escape. I can escape. So if the operating system dot path dot path dot exists, if the path exists, then we are going to pass the dest right there. So basically it's very simple. So if the path, remember which path that we set here, it should go to the output directory, and if the path exists, just tell us the file exists. Do not add new data set. Do not add new data set. Otherwise, before you print out that, you can tell us the size of the data set that we have. So the size is very simple. Get the size of that. And do we really need the size? And then we can return. For now, we don't need this. You can just comment it. We are not going to use it here. Whenever we need it, we are going to refer to it later. So after it's done, it's going to return that function. What else do we need? Do we need to add? So if it's downloading, after it's done downloading, we need to understand several things right here. So we can define a response to get the response from the data that we just downloaded. Very simple. So we are going to use the requests that we just defined right here. Then we are going to do what? To get the URL. Is it the URL? Then we can set the timeout. You know this thing can go for the longest. You can go for the longest. So we need to set it to 30. You need to set the that to 30. So we can also define the response dot raise for status. So we can check it if the request was successful. So basically this one is just check it out if the request that was downloading the data, if it was really successful or not. Okay. So if the request was really successful, now we can go and do something else. So what else do we need to do? Remember that we are just downloading the data. We are in the process of downloading the data. So we need to do what? We need to pass the OS dot make directory. Make directories, that is, go to the operating system dot path dot directory name that should remain to the data set that we just passed right here. Then if that exists, then we can set everything to true. Then we can write a loop here. So with open, let me just have this is okay. So we can use the file system that is right. So you can just basically go with open.write, go to the directory, then write that, then convert that into the UTF-8, that is the encoding. Then you can name that as basically as file. Very simple, file.write. It's basically using the word file.write, and then you can just write the text right here. As simple as that, as simple as writing that particular file. So in case we write that file, very cool. So it's very simple. Now we can return the main, and the main function will be downloaded, and this is the main function right here. So now let's assume now we run this code. That is the function for download. We just decide to run this function, or we run this code or this file. It should be able to download this data from Shakespeare, then it should be able to dump it inside our data sets. So it should be able to do all that. So let's see what next we need to do. We said it's we need data from ground up. Remember that we have downloaded the data. We need to prepare our data for training. Basically, we prepare our data for training. Remember that? So inside here, we are going to write a file that we are going to call it prepare.py. So it's going to run the prepare.py. Let's prepare our data ready for training. It's very simple. So we are going to, as usual, import OS. After importing OS, we need to import JSON. I'm going to explain why we need JSON. Then also we are going to import touch. We are going to import touch. So why do we need to import JSON? We need our AI to really understand what kind of system that we are working with. So for our code to understand really good, so that means this data from Shakespeare that we just downloaded, this one is a very normal text. So what we need to do is convert this into a JSON file, back and forth encoding and decoding of this particular content. So now that's what we are trying to do, prepare the data ready for AI training. Basically preparing and formatting the data ready for training. So we need several things here. We need the input directory input. So the input, we can call them paths instead of directory. Input path will be the data input.txt. The output path should be prepare. No, the output path, we need to change this to something else, and that will be the vocabulary.json. So we are going to, the output path of the data should be the formatted vocabulary. Then we need something like the train underscore path. The train path should be the train.pt, the trained file.pt. We're going to see what is the pt file. How does a pt file look like? So the value path will be basically the data val.pt. Remember, most of these files we don't have them. We do not have input. We do not have input.txt in which it should be created dynamically immediately. It should be created immediately the time that we run our code. Immediately we run our code. So that's it for preparing that. And we are preparing our data for training. So there's something we call training, the training ratio 0.9. So this is what happens in the training ratio. Very simple. We use 98% of the data for training. Then we use 10% to determine the evaluation or validation of this data. The data might not be valid. We might convert it wrongly. It can be wrong. So we leave some error rate there for us to make sure that this thing doesn't go wrong. Of course, it can't be 100% right. So it can go wrong. It can go wild. So error can go wild. So we need to make sure that is taken care of. So remember that we are working with the large language model and relies more on text. So if it relies more on text, this is something that we need to consider when it relies more on text. So we are going to write a function, and this function, we are going to call it escape. So we are going to create this function that is going to build the vocabulary. First of all, everything here seems wrong. Everything here seems wrong. It's not right here. The autocomplete is misguiding. So right here, we are going to convert our text. Yeah, there you go. We're going to convert our text right here. We are going to convert our text. That will be in form of a string. We are going to convert into a tuple, into a tuple in which is going to basically look like that, into a dictionary, as simple as that. So right here, after we convert that, so basically this one is basically trying to convert, remember this logic here. Let me see if we can get the logic. There's something that we talked about, the story. Which stage are we at? Let me see. Yeah, there we go. Teaching the machine to read via character tokenization. So this is the stage that we are at. Basically converting every single text that we have into what we are calling converting strings into integer and integer into string, converting into machine language and then back to human language that people can really understand. So that's the logic that we first want to build. So this is very simple. We define the characters, and the characters should be sorted. So should be first of all sorted. Let me just do away with that. So we are going to get the characters in the data. So what characters do we, what do we mean by characters? Let's say we have the world, hello world. For example, this is the hello world. So that whatever we are trying to do is basically sorting these characters first of all. We sorting them into single text. We are trying to sort that. So we implement the um story. It should look like this. So oops, escape. So basically it's trying to enumerate these into character, basically tokenizing all this using this basic knowledge. So if it's a hello world, it's going to convert that into that dictionary that we just said right here, right? Then it's going to basically convert that. Let me see if this one can autocomplete again and try to get the logic. So basically it's just looking like this. It's just converting any text. For example, hello world is just making sure that this looks like this. Extract each character, then assign into a different machine language for it to understand in simple terms. So this here is basically trying to do this. Take the whole text, then try to make it look like this. In simple terms, that's what it's trying to do. So remember that we said we need to encode the text and implement the logic to decode, as simple as decoding all this. So this one should be the vice versa. This one should be the vice versa. So what is the vice versa here? It's basically just reversing it. Reverse whatever you tried to do. Reverse whatever you tried to. Reverse whatever you tried to do now. So are we reversing it? Basically, you check this. The first line here is basically taking hello world, then convert it into this dictionary. Then for it to be decoded, you just do the vice versa, encoding and basically decoding. Basically, this one is converting from integer into strings. So in case you're wondering what words are these, this one, string to integer, basic variable names, integer into string, basically integer to string, integer to string. So it's basically doing that logic. Now I can return all these functions right here. So I can basically return it right there. So I want to build the logic to do what? Now to do the encoding. So remember that we just defined how this should happen. Now I want to define the logic now to do the actual encoding. So we need to use the keyword encode, right? We just write the function encode right here. So it's going to convert string, anything from string and also into dictionary, into a form of list, as simple as that. Then we are going to return whatever it encoded right here. So let's see. So basically this one is character. In case you're wondering what is the meaning of this C and CH and I. So basically this stands for character, this one stands for integer. For any character in integer and vice versa. So in case you're wondering what kind of words are these, this stands for characters and integers. Integers. CH, character for cha, character. Then remember that because we did encoding, we need to define the opposite now. And the opposite will be decoding. We just encoded. Now why can we decode? Decode for any IDs. I don't want my code to be so huge. Let me just convert that into IDs for any indices. For any indices. So basically it's doing this, huh? Very simple. It's doing this. It's converting now. It's trying to decode these indices right here into a string. Remember what we did? Because it's not has been assigned into characters. Can we decode and rejoin whatever it's right there? Yeah, we can do it. So we decode that. So whatever text that we decoded, now we can join. By using the word join, it's basically joining H, he, L, O to make the word hello. So it's trying to join that functionality. It's trying to join that function. So it's basically trying to join everything together. Now, because we have joined that, we have prepared our data ready here. We need to do preparation of the data. Remember that we are preparing the data for training. For our training, we are very far away from training the data. First of all, we are setting up the ground. We are setting up the ground, collecting the data, formatting the data, tokenizing the data. That's the stage where we are at. So that now we go to the other stage of now joining all that together and training our model. So we can define function that we are going to prepare. So we are going to prepare what? We are going to prepare the input path. Input underscore path. The input path, which in our case is a string, then that we assign it into the input path. I'm going to put that into none. So this one should be the input path, and the input path should be here. Yeah, I'm spelling input path. Yeah, there you go. The input path. Let me see if we have anywhere. Yeah, it's going to take the input path. So first of all, we are going to take the data that we are going to input it. Then we are going to catch errors before they actually open. So we are going to define a variable that is as simple as this. So if the file, if not part, oops. So we are going to oops, what's happening here? So we are going to check if these files exist. So that's why we are calling the file not found error. That's why we are raising the error message. That is the error message that is the file not found. So in case we are trying to fetch any file, it's going to tell us that the file is not found. In case we are trying to train any data, then by any chance we do not have any file, it's going to raise the file not found error. So this is basically the database that contains our data. Basically, it's the database that contains all our data, right? So, so if we prepare our data right here for training, first of all, we check if files exist. So if that file doesn't exist, now we can open our file. So you can open with, let me see if this is the correct thing. Yeah, basically this is simple. So you remember the input path. The input path was the data that we inputted here. The input path of our data was the input.txt file, right? So this is the database that contains all our data that we need to train our AI with, right? But in our file, basically it's basically a file that we are referring it as a database that contains all our files. So we are going to open our file in read mode. R means read mode. If you read the file systems in Python, you are going to find that we have the R for read mode. Open the file with intentions to read the data from the file. So, and we use the encoding technique, that is the UTF-8. Then we open it as a file. Then we are going to return the text.read file. Remember, first of all, it's in read mode, so we can read it right there. As simple as that. I don't think we need to print the file. Now, because we have prepared our data, we have opened our data, I want to do something that we are going to call it building the vocabulary. I can build vocabulary. So let me explain what's happening here. Remember these functions here that we used here, the story and itos, and they are right here. We defined them here. We defined them long time ago right here. So because we defined them right here, they are right here. That's whatever we want to use. Remember the build vocabulary function that we created right here? It's now time. It's now time to use that vocabulary, that function that we just created right there. So right here, we are going to print, no. We need the vocabulary size, vocabulary size. And the vocabulary size, we are going to get the string to integer. The vocabulary size is basically the string to integer that it just converted right here. So that is the vocabulary size. Maybe in case we want to see it, we can basically print the unique characters right here. Is it the unique characters? You can just call it vocabulary size. Vocabulary size. The vocabulary size, in case we wanted to see the vocabulary size, we can print it right there. Just in case we wanted to see it. Now, we need to do other function that is open. We need to open another file that will be basically the vocabulary path. Let me see if this code is correct. Vocabulary path. Do we have this really? The vocabulary path. Let me check. We do not have the vocabulary path. Yeah, this was the vocabulary path, not the output path. Vocabulary path. That's why it's not working. It should be the vocabulary path. Let's use the correct variable names. So this is the vocabulary path. So whatever we need to do here, or whatever we are trying to do right here, is remember that we have a file system that we are trying to figure out what do we do with it. That should be used to train our AI, decode the data, give output. That's what we are trying to do. So the moment that we open the vocabulary path, that converted it into JSON, that was fed in terms of JSON, we are going to write more vocabulary inside that particular file. So we are trying to create patterns in which we are going to we are trying to create patterns in which we are going to add this data into all the vocabulary. So whatever we did right here is, see this JSON here, the vocabulary that we are just building. So we are going to take the JSON. First of all, we are going to convert into JSON dot dump. Dump is just taking take, add data right there. Dump it, and you should add it in a format or in a simple way that you are going to do it. So we are going to dump the string to integer, right? That is going to right there. So it's basically a JSON file, and it should have the value, and then we have right here whatever we are trying to dump. Then the integer to string, you're also going to dump the integer to string right there. But before that, before we close that function, let me see, let me confirm something. We are doing the right thing. No, right here, we don't need this. Yeah, we need it. So you see this integer to string that we are just converting. We need to convert it into string. After you convert it into string, let's just assign a random variable that we are going to call it kv, just random variables. Let me see. Let me read this code first of all before I approve it. Let me read it. For any k, for k in v and v in what? In items.items. It is correct. Basically simple. Yeah. No, so basically this code is doing basically these are just variable names. You can name it whatever you want to, whatever variable name that you want to name it. There's no special thing that we are naming right here. It's just AI naming whatever we tried to name right here. So whatever we are doing right here is very simple. The vocabulary part that we have, or our vocabulary that we converted, very simple. We are going to dump everything right here, dump into that JSON file. And you remember where our JSON file is? It's called vocabulary.json, vocab.json. That's where we are dumping all these items into it. And it's a file system right here. It's a file system right there. But in case you want to print out the vocabulary, for now we don't need to print out the vocabulary. We don't need to print out the vocabulary. So we are going to encode the entire data set right now. So how do we encode the entire data set? It is as simple as data dot no, actually this is the wrong variable. So we are going to use the torch. Let me see. Do we have torch here? Yeah, we have torch. So we are going to use the torch.tensor.encode, okay? Dot encode the text and the story into data types that is the long type. So basically what we are trying to do here is trying to encode the data. In simple terms, let me explain what is encoding. Encoding is as simple as here. Take a hello world, convert it into, try to tokenize it into something that is easy to understand for machines. Very simple, convert it into that integer, convert it into integer. You convert it into an integer. So after we convert it into an integer, we need to do something extra. Very simple, nothing complex, very simple. What do we need to do? Do we really need to do this? I'm not sure. Let me check. What exact variable can we name here? Anyway, it's not going to be big, so it's fine. We are going to convert the data into an integer, then we multiply by the train ratio. The train ratio. So where are we getting the train ratio from? The training ratio, we are going to get it right here. The variable that we converted here into training ratio. And whatever we said with the training ratio, in case you're wondering why the training ratio. So what we are trying to do here is as simple as this. See the data that we have. Let's assume that we have 100% of data. 100% of data. Then we assign something that we are calling training ratio. Why 0.9 and not 0. And not 1? In case you're wondering, what is this 0.9 standing for? Basically, it's 100%. So we represent it as 100, we represent it as 1. So what is 90% of 1? It's 0.9. So instead of 100%, we can represent it with 1. So zeros and ones. We can just replace it with 1. So 0.9, it's 90% of the data is going to go to the training, then 10% is just going to go for validation. It's just going to go for further validation. In case you're wondering what's basically that. So after we do this, after we try to encode this data and split that data, then we are going to do training data, training underscore data. We are going to define the variable for that to be as simple as this. As simple as this. So let me explain what's happening right here. In case you're wondering, what's happening with this code right here? I really don't understand what's happening here. It's very simple. So this is the training data. From the variable training data, then this is gone for the validation data. So we can as simply as represent this. Let's say I can rename this variable to, let me data splitting, to something that makes sense. So this one is going to go to the data splitting. Data splitting. We are going to rename the n and whatever we are trying to do. So the data splitting here, that's what happens. We said we have 100% of data, right? So in 100% of data, it is very simple. So whenever we add this full colon, then go to the data, the variable name is on the right in layman's terms. Then you see this one is the opposite of that, the value. So we are basically splitting the data into two. First of all, the training data, the data that we are going to use for training, the data that we are going to use for validation is basically using the same. To make it shorter, we can return into the n. It's basically splitting that data. So it's basically assigning. It's basically assigning the data for that. It's basically assigning the data for that. So after we assign this data for encoding and everything, we can do something really simple right here. So we can do something that we are going to call it sanity check. Sanity check. There you go. This thing understands me anyway. So for sanity check, whatever we are trying to do here in sanity check, we are going to assign random values. Basically, random values. So we can define something called sample data, in which, remember that we had text, I can assign to any random value, man. I can just assign to any random value. Just checking. This is for, it's not necessary, but it's also for, it's just like error handling testing, if it's really working, basically enforcing everything, as simple as that. Encoded, you can call it encoded sample, decoded sample. So for the encoded sample, we can define a variable that is called the encoded sample that we are going to use the encode. Then we are going to pass the sample here. Then we are going to do what? The store, the string to input. The string to integer, not into input, the string to integer. Then on the decoding sample, then on the decode sample, it's going to be really simple here. We just use the keyword decode. Then encoded sample, we use the encoded sample. Then we convert it back to integer to string, integer to really string. So basically this one is just for testing. So basically what we are trying to do here, the assert, in the assert, we are going to basically test the sample. That is the sample of decoded, should be the opposite. Decoded. Yeah, it should be the decoded sample. Then we pass the sample here, and then we check encoding data mismatch, anything. This one can work. This time around we can print out, man. We don't need to. Encoding data and sanity check passed. Yo. This one is just basically for testing. It's basically for testing. You really don't need it that much. You really don't need it. It's just for testing. It's sanity if it can check it can pass the encoding and decoding and also assigning the data for training and all that kind of stuff. Save, train and validation data. So you remember this data that we encoded right here. This data that we splitted into training and the validation data. So we need to save it. We need to save the data. We need to basically save the data. So we are going to save it with the tensors. We are going to use torch dot save. We are going to save the training data into the train path. Then the validation data, we are going to save that validation data into the validation path. So very simple. In case you're wondering, where are these paths? The paths are just complicated words. The real words are files. The real words are files. In case you're wondering, we just said training path to be training.pt. This is a type of file. Validation data to val.pt. In case you are wondering, it's nothing complicated, just defining the path. So we are going to save the data that we just splitted in two different files, basically in two different files. Then imagine this function is complete. There we go. Then we can call this function right here. And a whole function is complete. A whole function is complete. So far, we can do a quick revision. What have we done? We have done the data downloading and data preparation. Data preparation. So what is the next step? Let me see the next step. Data loading, yeah. Data loading. So what we have done here is basically two things. We do not have any data. Let's download the data, ready for AI to train. We formatted our data, everything. We made sure our data is perfectly clean, well arranged, everything. The data that we just stored, we prepared it for AI to train, split, and do every activity that it needs to do, right? Then after that, we did an extra step. We need to do the extra step. Remember the data that we downloaded, prepared? We need to do what? We need to load the data now. Data loading. That's why we have this step. That is data loading. Basically, this is the architecture. One by one, process by step by step. So we are going to define the loader.py. That is the loader.py. It's very simple file. Loader.py. Inside the data, it's loader.py. Anyway, are you guys still here? Are you guys still around? Or you guys are floating? Or you guys are still floating? Don't need config, don't need train. Are you really here or you are floating? Are you somehow floating or you are here? Anyway, guys, you can say hi. You can say hi on the chat. We can know where you're watching from. You can say hi. You can say something on the chat. So let's do this. Let's do the loader.py. The loader.py. The loader.py. First of all, PyTorch is really used in every stage of our file. Import torch. Oh, I did loader.js, man. I'm used to JavaScript a lot. Wondering why. Loader.py, not JS, sorry. I'm used to JavaScript every single day. So we are going to import the loader right there. Going to import the loader. So our data is ready right here for training. Now, you guys, you can get the link on the repo. You can get the link on the repo link. It's right here on the chat. You can check it out. The GitHub repo link is right there on the chart. Check it out, guys. Check it out. So let's continue. And now prepare the data loading. So data loading, because it can be a lot of data, we can have thousands and thousands of files. So we need to get the data into batches. You need to get data into batches. So inside our batch, it's going to have several things right here. So it's going to have the data that is the split data, the split that is in form of a string, the training data, train underscore data into torch.tensor, load it into steps, thank you, it's now understanding. The value data, validation data, same. The block size should be in a form of integer. The block size as well, batch size. The batch size and block size. Also, we need to get something. You remember we defined the device, our device, so that it can know the capacity of our device, so that the moment it's loading the data, does not overload our system. So we are going to define the device right here as torch.device. 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 No, or maybe we can get it in form of a string. I think it should work well. This one, we can leave the 2 to be tensor. Just like that. Just like that. Yeah. I don't know if this is correct, but let me check. Get the batch size, convert into tuple.tensor.torch, tensor.torch. Looks clean to me. Yeah, it's perfect. So right here, after we do this, we need to convert, you need to get this data into batches. It is as simple as data assigned into the training data, and then we check if the split data is assigned to, I need to use into the training data set, then else as the value data. Anyway, let me explain what's happening right here. Very simple. We want to get the data into batches for us to train our system and to make it work, right? So the data that we are going to get into batches, we are going to get the training data, and we check if it's already split into our training. And then remember that whenever we were trying to define our data preparation, whenever we are trying to prepare our data, we defined all these kind of things: the training, how we download our data, how we prepare our data now. So it should be ready for training. Otherwise, you can get the data into different places. So for example, take the data, the training data, if it's in the training phase. Otherwise, you can get the validation data. So we can find the index on how it gets the data. So basically, this works like this. Let me just tab and then explain what's happening here. The index, we need the x and y axis. then the device, then return. Do we need this? We don't need this. So let me just cross check data. It's the integer, the block size for I in index. Then you get the next stack. Then you add one, the block size. Yeah. So very simple. So this is what happening here. You can define a variable ix index, take the touch dot random integer then you take the data that you just loaded right here, either if it's in the training data set or it's inside the validation data set. So if you have taken any data or you have fetched any data inside the tool, you can do what? Just make sure that you take the first chunk of data, then you minus the block size, then the batch size. So this is what really happening here in this value here. So let's explain this, what's happening right here. In layman's term, let's draw a graph. A graph has x and y axis, right? A graph has x and y axis. So we need to stack our data. We need to keep stacking all these kind of blocks, depending with how our data is really like. So first of all, we get our first block. We first our first block. I will explain with raw data of how it works right here. I will explain with raw data how it is really joining the dots. How it is really joining the dots right here. Then you can define a variable y, then you start the data, and then you just want to add one block size on top of that particular data. So let me explain with the diagram how that is really happening. So this is what's happening in simple terms. Now, we want to load our data. Remember, we can have so many files or so much data, and we can't load it into our system because it might be large. It might be really intense for our system to handle. So we don't want our systems to break. So because we don't want our systems to break, it is very simple. Load the first chunk. The moment you load the first chunk and you are done, load the other chunk of data, all the way to the final blocks of data. So what we mean by block size can be, data can be, let's say, 100 MB. That is the block, the batch size. Then you load another batch size with 100 MBs of data, then other 100 MBs of data. Maybe you have like 1 GB of data. So how many batch sizes are those? Like 10, because you have loading into, you just take 1000 divided by the batch size of data. The data, one data batch is 100 MBs, just like that, the batch size. Then, but we have something that we are calling the block size. The block size. So you can load the batch size, then you check the block size of that data, and then you return your data. You return your data set right here. As simple as that, as simple as that. So the moment that you are returning right here, we need to re-edit this. You return x dot to device, y dot to device. So y, you remember this device right here, y dot to device. So why are we returning this? Basically, this one is simple. We are defining our device because We are defining our device because you remember that we said we don't want to overload the kind of hardware that we have in training the AI. You guys who have heard about OpenAI and how they really rely on NVIDIA for chips. So we don't want our machine to overload its task. So we are defining the device. First, understand what device are you trying to run this model on. Get the chip size, the type of chip, then know how to segment the batch sizes. So basically know how to segment all those batches. Um, Jackson from Malawi, you are trying to wonder what we are trying to do. Yeah. So we are trying to create our own AI from scratch. Basically, you have wondered how ChatGPT works. Using that ChatGPT example, so we are trying to get raw data from books, from blogs, take that raw data, dump into our own written code, run the training, and see if with our own, if we can try to build our own AI from scratch. Basically AI like ChatGPT, where you can just text it anything, then it gives you an answer. So that's exactly what we are trying to do. And we have defined steps in which you need to do for you to come up with a complete AI system. So for you to come up with a complete AI system, so far we have determined we have steps. You need to have the data. After you get the data, you need to prepare the data for it to be trained with AI, for AI. After you prepare the data, that is the data cleaning, arranging the data. We converted our data into a JSON format. So after you convert our data into JSON format, we need to understand. So we need to prepare the data. Data preparation is the stage where now we have converted our data into JSON. We have tried to tokenize our data. We are trying to convert anything that is unmeaningful um, into machine code, into zeros and ones, so that whenever we are trying to train the AI, now it can understand all that. So we are defining all those different steps one by one. So basically, we are in the stage of where we are loading data. So we downloaded the data, we prepared the data, then we are loading the data into, we are preparing the data loading into our system, ready to train. And that's exactly where the stage that we are at. So yeah, so basically that's the stage where we are at. Let's see what the next stage. Anyway, guys, in case you're wondering if we can build an AI model in one day, you're not going to do it in one day. You're going to split it into several days. So basically, this is part one of it. This is just stage one. This is just day one of creating AI from scratch. So we have prepared the data. What is the next step? Data loading. So let's see, the next step is building the transformer models. The transformer, building the transformer. So, so what is a transformer right here? In case, before we go to building the transformer, before we go into that stage of building a transformer. So a transformer, we define it as the heart of the project. The heart. The heart makes you breathe, gives you life, in short. So in this stage of building the transformer, we are trying to do what? We are trying to build each component individually, then assemble them into a complete model. Every piece, we are going to explain each piece or each stage one by one, each stage one by one. So, so we are going to use something that we are going to call it self-attention head. So self-attention head is how the model decides which other tokens are relevant when processing each token. So think of it as each word a model asks which other words to pay attention to. So a transformer here is very simple. Let me explain in layman's language, in layman's terms. Let me find an empty file like this. So an empty file like this can have things like, now this is how AI thinks. This is how AI thinks. I want to explain this in a very good way. So this is how it happens when AI is trying to process tasks behind the scenes that we don't understand or that we don't see, or the part that we have never witnessed or we will never see. So this is how it happens. The moment that you write the word hello, I think we had a diagram here that explained how that works. Let me see. No. I had a document that explained how that works. There we go. So the moment AI is trying to think, we tend to think it's thinking. So the moment that you ask it, for example, hello. When I say hello, then it thinks and gives me the feedback. Hi, what's up? How can I help you? So this is what happens behind the scenes. So it's trying to figure out. Yes, you asked me hello world. How should I respond? Then it will go inside the trained model, inside the available outputs or possible outputs. Then it'll try to do what? It will try to write. It will try to predict. Yeah, the keyword is predict. So it will try to predict. I want to say hello back to this person. So it will write hello, age. Then it will try to figure out, oh, what other word do I write that makes sense or that can really match the output that I'm trying to do. Then it will read the pattern and then it will find out it needs to write he. Then it will think the next step. What else do I need to do? I need to think, and the pattern that fits, the keyword is pattern that fits, is L. Again, think, find the pattern is L. And think through and find the pattern is O. Then it needs to think, I have constructed a whole sentence, right? A whole word, not sentence. I need to construct a whole sentence now. If I need to construct a whole sentence, what happens? I need to write hello, give some space, then continue with the thinking pattern. With that thinking pattern. Then that happens over time and over time over time. So that's what exactly these transformers do. That's why we are calling transformers at the heart of the project. Basically, it's trying to figure out what other words do I pay attention to. So basically, what other words do I pay attention to? So now take that scenario and replicate it after training the models with billions and billions of data or billions of parameters. Now, if you replicate that, now that's what models or these transformer, basically these transformers, what they actually do. So we need to do the attention dot py, the attention dot py. So the attention dot py, remember this is the model, control B minus. So this needs to go to here, attention.py. Attention.py. So this is the attention.py. Now we are going to do several things here. Attention.py. We are going to import the math library. We are going to import torch as usual. We are going to import import torch.nn, the library. Then we are going to import torch.the functional transformers. Yeah, that's what we need to import for now. So over here, we are going to, we can write this in form of classes. And we are going, remember we said we are going to define it into attention heads. So nn.module n1.module. I think module should be caps n. That n.module. If we define the attention head, this one, I don't want to autocomplete this. So attention blocks. No. So I can just define this method right here. We can define the self. We can define the head size, in which it's still an integer. The block size, yeah, you need to define the block underscore size, which is in form of integer. Then we need to import the dropout. We are going to explain what is dropout, which is float. Is this really the correct thing? Let me see. And size bias false. Yeah. So we are going to define several things right here. So do we need super? Yeah, we can import the super method here. It's the method. So we need to define self.key, which you are going to pass the key later. Then we need the linear model here while we are defining our transformer. Then we have the head size. Then the head size. And the bias. Do you need two head sizes? No. This one should not be an head size. We can't have two head sizes. We need to import something like an embed. Is it an embed? AMD. AMD. An embed. Where is the an embed? We have the head size, we have the block size. Yeah, we didn't define the n and bend. These are just variables. We have the n and bend. Anything else that we missed out? Yeah, we missed out this float should be 0.1. Be 0.1 into 1 decimal place. So we need to change all these head sizes into we need to change this into embed size, the head size bias is equals to false. So we have the self.register buffer util. Use no, we don't need this register buffer right here now. For now, we need to the query, the value, then dropout. It's equals to the nn dot dropout, which we assign it to the dropout layer. The dropout should be here. Okay, we have the head size, and then the block size, in which we are going to use it later, the dropout, okay. Then you can define another variable, right? In another function here, define function forward. Let me see what we have in function forward. You have the self.tensor, that should be equal to tensor. So we are going to define this. We are going to explain what this does. DTC goes to shape, compute attention score. Do I really need this? Let me tab and see what we have. I really don't need that. Really don't need that. So we can define variable BTC into X shape. Okay, let me think first. Okay, dot self dot. Where is this X coming from? We defined X dot shape. Let me think. We really need this or not? Yeah. We have the key that we defined right here. The self dot key. The self dot query. Well, the self dot value. We need it. Remember, this is converting into tensor. We need the head sizes. The head size. Yeah, we really need these. Just need to rename these variables to meaningful variables so that we don't get confused. Maybe I can compute the attention score so that I can understand this. Just depending on that autocomplete. No, I don't need to compute attention score. I can do, I can try to do the scale, that is the math. Scale is equals to math dot square root k root of k dot shape into 1. And you have the score, the attention score is equals to q at transpose -2, -1. Okay, so basically what I'm trying to do here, I'm trying to draw graphs on the output, how our AI is going to get the out. I'm just trying to evaluate the model first. I'm trying to evaluate the model first and see the graphs. How good is our model, so that we don't release it without testing? How good is our model, the training scores, and then the graphs. So first of all, I'm going to define the scale. Then we're going to define the score, in which is going to depend on the query and also depend on the k dot transpose. Then you divide by the scale, in which the scale is the square root right here. Okay. So after that, what else do we need to do? It's getting more complex as we go on. Designing these models, they get more complex as we go on. This one should be scores, several scores, not one. So I can do the scores. The scores is equal to scores dot masked fill. Masked fill self dot trill, in which self dot trill self dot trill, I'm going to see the training. As well as that. Let me see if this is really correct to 0. Okay, so you remember this syntax here when we were defining about data preparation. Was it data preparation? Yeah, there you go. Was it data preparation? Yeah, let me see. Data loading. How did we define this? Oh, you have the loader. Not actually in the loader. I want to see where we defined. It should be here. Yeah, it's here. You see the training ratio that we set to 0.9. So this is exactly whatever we did right here. So we assumed 100% of data. So after assuming 100% of data, this is what we did. We took that data and splitted it into two. Into the training path and the validation path, in which the training path, all the data that will be used for training, was 90%. Then the 10% that was 0.1 should go to the validation error. And then we assigned it here, exactly here. And we assigned it right here. The validation, the training, and then you have the validation error. Basically, this is just defining ratio. Yeah, if you know, you remember ratios in mathematics. In high school, ratios, also in campus, people learn ratios, depending with the course that you have done, of course. So here we define, or we assign it into ratio, just like assigning into ratio of 3 into ratio, 3 into ratio of 8, whatever that means, just assigning it into 3 into ratio of 8. So basically this we are assigning int into ratio of 0, then 0 into ratio of 8. So instead of writing it 3 into ratio of 0, like for example 0 into ratio of t, just leave it blank. Just leave it just like that, and then it will automatically know whatever ratio it's been assigned. Then assign that. Actually, this is one of the hardest parts, that is creating the attention and defining of the models, the transformers, not the models, but the transformers. One of the hardest parts. Not hard, but mathematical parts. Now, that's where now AI, the mathematical part of AI comes to play. Softmax to get attention there. So we use softmax to determine the weight or the attention weights of these models. So we can define the keyword weights is equal to the attention score. Then we use the softmax. Okay, let me check. Do we really need to use the softmax? Okay, let me see. Do we really need to use the softmax? What is softmax? Let me quickly Google here. Softmax. Okay, let me check what is softmax. Let me check if we need to use something else. Okay, yeah, we can use softmax to calculate this. So in case you are wondering what is the softmax doing here, softmax basically means acts as like the judge. Softmax acts as like the judge who determines who basically determines how much focus it should pay attention to whenever it's training this model. So softmax, you can just in layman's terms call it the judge who is determining how much attention it should pay to certain words. For example, if remember that whenever you are trying to create a pattern of how AI should respond, hello world. So it's trying to determine the next word that it should pay attention to. So softmax, it should be used as the judge to determine how much focus do I pay attention to the next word that I'm trying to output or I'm trying to focus on. So softmax basically works as that. So we are just trying here to calculate how much attention do we pay to the output that we are trying to get. So it's very simple. Before I write any text, or before let's assume, let me think of something. Whenever you are trying to construct a sentence, in our head, this is what happens. We have the words that we have said. Then we have our words that our brain is paying more attention to say next. Okay? So this softmax layer here, it's trying to, as I speak, my head should be constructing this next sentence that I'm trying to speak. So it should also pay attention to whatever I'm trying to work on next. So softmax basically is trying to calculate how much weight, how much force do I really need to, or how much attention do I really need to pay to the next or to the next word or to the next prediction that I'm trying to do. So we can do the weights. Weights. We use the self dot dropout of the weights. So basically, this is simple here. So here the dropout is calculating the loss. Hi Francis Jogona. Welcome Francis. So when we calculate the dropouts here, it's trying to determine, yes, I've paid attention to the next word, but how much have I lost in the process of pay attention to the next word that I'm trying to predict? So also the weight is also trying to calculate that. So whenever you're trying to calculate that, this is how you calculate it. Out of 100% of what I should have paid attention to, how much did I pay attention to, and how much did I not pay attention to? I paid attention to 80%. 20% I didn't pay attention to. Basically doing that. That's what we are calling the dropout. Is the thing that I've not paid attention to. Okay? Very simple. Then we can get whatever weight. Yeah, is it weight? Whatever weight and that is the value. Yeah, this is the value of x. So we get the out, and then this is nice time to return out the output. Basically, this is basically the output. Just write in some words here. You can find out the best variable names to use for this. Now, when the systems gets way complicated, this one is going to do us some dirty work here if you don't clean the code right now. So we have paid attention to that. So the last thing, isn't really the last. So it has paid attention to one head. Okay. We defined four. Do we need to define the next one? Define function. No, we defined this function, so this one is complete. So we define the next class, mode head attention. Mode head attention. This one should not be hard because let me see. We have the function, the number of heads. Really? Self number of heads that should go to init head size, init, and then init block size, the dropout float. Basically, we are just copying everything here. See everything that we defined right here. Nothing new. We just define exactly how it was here. But what we change is the heads right here. So at self.heads is equals to no, your sign is not equal. Why am I? My mind is ringing mathematics right now. So you are assigned to the module list. This one should be head size, the number of embeddings, the block size, the dropout layer. For anything in that range of number of heads should work. Yeah, it's fine. So self.projection. How is it projecting this? Projection. How is it projecting this? So it should be linear regression. So the linear, it should think in a linear way. So the number of heads multiplied by head size, okay, think this one should work. Anyway, in the process of testing, we shall find out if this is really doing the actual prediction. The number of heads. So also we calculate the dropout. Dot dropout. This is equals to the dropout. Remember that we have chances of our AI missing some things. In the process of training, it might not train 100%. So that's why we always have the dropout. Module adds dropout, yeah. Number of heads. Now, in the process of linear, I doubted this, so you don't need that. Oops, you don't need this. Okay, remember I calculated forward here to calculate how the graphs are going to look. How are we going to determine the weights of the model? How much is it losing? How much attention is it going to pay to the next prediction? So we are going to use the same forward. That is self. You can write function variable x assigned to touch dot tensor. Okay. So we pass the output. The out should be out.cat h dot. Let me see. Let me think. Let me inspect this code again. It's AI generated code. Let me inspect. So it should do that for any height in self.heads. Then we dim with -1. This one looks good. This is a lot of work. Why can't self.projection the dropout? No, this is not cool. We can just combine that code into one. Self.out. Then we combine self.project into output. Instead of writing 2 lines of code, we can just do this. You are lost. You are lost. Okay, Francis. Worry not. Worry not. So, maybe to explain whatever we are trying to do here, we are trying to build the brain of this AI. So in this brain of this AI, what it does, in layman's terms, we said with the same example, whenever you are trying to speak, we have the words that you have already articulated. Then we have the next words that you are projecting to say, or the next statement that you are projecting to say. So that's what we are trying to replicate, that functionality in our own brain into machine code now. So the moment that, remember there is whatever I need to say in my head, I have 100% context in my head. But in the process of spitting that out, I can miss some things that I won't say out. So the things that I've missed out, that's what we are calling out the dropout. So I'm not saying 100% whatever is in my brain. I'm saying 90%. So that becomes the 10% becomes the dropout. So we are trying to replicate that same thing in our head to work in computers. So that's what we are trying to build right here. So that's exactly what we are trying to build right here. So let's do this. Let's do this. Yeah, we might not complete this today. It's going to be a series of several live sessions. So this is just session 1. Okay, let's continue. Let's continue and see how much can we stretch this. How much can we stretch this? In case you want to get the repo for the ready build system, you can check out the description. You can check out the description of this video. Down there, you are going to get the code base, the link to the repo for the code base. So you can give me a star whenever you access the repo. Give me a star. That would push a lot. Also, feel free to subscribe to the channel. Subscribe to the channel. Anyway, we are going to build that function alone. Only the mode head, because this is a lot of code that we need to do. We can't build it. We'll move it. I think we can stop there for today. Let me see. So next, we are going to build later, maybe in the next session, probably on Wednesday. When is Wednesday? Wednesday, 4th of March. We are going to build a functionality that is, we are going now to build a complete network of AI. So we are going to build a class. We are going to call it feed forward and that module. So we are going to build this. Then we have two functions that are remaining. Then we are going to class of transformer blocks. We're going to build the transformer blocks that we are not going to build for now. So these are the next functions that we need to build. Let me see. Actually, they are very simple. Actually, we can build them before we leave, so that we do away with this attention layer. So let's just build it. It's very simple. Actually, it's not big. So it looks something like this. Very simple. So we can just define, because we already understand whatever this is. Now we define our main method right here with self. Got the number of embeddings here. Feed forward, we are just calculating most of the dropout layer. Then you calculate the float. You can define this as a super function method that needs to be used. Okay, so we can define a network right here. That is the self.net. Basically, this is just predicting how things are going on right here. The feed forward class here. So in our case, because we are trying to determine so many things, how much loss do we have? How much are we losing in the process of training this AI, or in the process of trying to predict the next word? How much are we losing? So we can define a function self.net. Then we are going to use the sequential model. Then we are going to use the ReLU activation. Didn't need ReLU really. Just a moment. Let me ask Google, do we really need ReLU? I'm not sure if we really need to use ReLU or we need to use any other activation layer. Hmm. Let me find out if we need to use ReLU. Yeah, we can use the ReLU instead of the softmax. You remember the last one we used softmax, so we can use ReLU in this case. Okay, so yeah, we can use the ReLU. Basically, the ReLU means the linear rectified linear unit. This is the full word is rectified linear unit. Basically, it's now let me, how can I explain it in simple terms? So the ReLU basically, I want to find the simple terms that I can define ReLU, rectified linear unit. Okay, you remember that in the process of training our AI, we are losing a lot of context in this space. We are losing a lot. Yes, we have defined it to go to 90 and 10% of the data that has been divided, but in the process, we are losing, we might lose a lot of context in the process of predicting what next word we say. So to avoid that loss and to reinforce that we don't lose a lot of context in the process of predicting the next word, that's why we are using the ReLU, the rectified linear unit, to predict basically to predict the next words. So in this process, we are basically trying to rectify. Yes, you are trying to predict the next one. You are losing a lot of attention, but can we rectify that in the process of predicting the next one so that we don't have a lot of loss in the process of getting a valid feedback? So that's what we are trying to do. Basically, trying to rectify. Don't lose a lot. You have a lot of context. Kindly don't lose a lot of context in the process. That's why we are enforcing it with the rectified linear unit um, rectifier here. So in the process of that, we can do the define the function forward, in which it should go forward and determine what process does it need to do. Tensor. Basically, we are calculating the loss. It's mathematics here. We are calculating the losses and everything. So that's what we don't want to have. We don't want to have a lot of losses in the process of this AI. Then yeah, now we can finish this function, this particular functionality. Oops. We can close this with now building the transformer blocks. Transformer blocks is the last step. So let me see. Let me just tab and try to think if we can define all these process right here. So as usual, we have the super method here, init self.embed.init, which is an integer. We embed integers. The number of heads should be integers. The block size, definitely integer. The dropout, the 0.1, that is the 10%, in case you're wondering. And also in form of one decimal place. Let me see. As per function. So the the head size is the transformer block. We take the head size. How do we calculate the head size? This one in modulo of this. Soft.sa soft attention. The head attention. Let me just confirm. Self. You have block size. Yeah, we have block size. So everything is correct right here. Before I explain what's happening, the feed forward. Yeah, there you go. So basically what it's doing in this code base here, we want to calculate the head size. So we take this self attention. You can just write it as self attention, but we can write it as SA. I'm the only maintainer of this code, so I can figure out what is SA. So we take the multi-head attention. You remember all these function that we wrote here, the multi-head attention. We take the multi-head attention, in which it should include the number of heads, the head size, the number of bendings, block size, and the dropout for us to calculate the transformer blocks. Then we have the self.feed forward. In case you're wondering, FFWD is what it is. It is feed forward. FPS highlights, hi bro. So we have the feed forward. You calculate the feed forward, and remember, whatever you calculated in the feed forward, we want to make sure that we don't have a lot of loss in the process of predicting what is the next business logic. So the feed forward here, you take the number of embedings, then also the dropout, then the self linear attention 1, linear rectification 2, the layer normalization. We normalize. This is basically normalization, normalization. Then we embed this. Is this really correct? Do we need to use the layer normalization? I think so. But in the process of testing, we shall figure out if it fails, we can use another module, another transformer. So we have the forward, we calculate the forward, basically go ahead and do whatever we want. So we define x is equals to x plus the self-attention, in which it should include that x self-feed forward linear attention 2x. So the first one here, in case you are wondering what it's doing, in case you're wondering what it is doing, is it residual connection? Basically, this is doing the communication between the head forward throughout and this one here. It's doing the communication between the head. It's basically thinking. So yeah, in the process, let's explain whatever is happening right here. In case you are wondering what is happening here. So we have the self-attention that is using the multi-head. That's why we are using the self-attention here. So the self-attention right here, it's trying to predict what is the next output. So basically this is the one that is going to predict the next output or give you the next output. But in the process of giving the next output, remember we said that our AI is doing a lot of thinking, trying to predict. Okay, what do I say next after a certain word? So that's what it's trying to do here. And the feed forward, you remember the feed forward here that we said, it's making sure that we don't have a lot of loss in the process of giving output and also in the process of predicting what is the next thing that I should say. And that's what it's trying to do here, building now the brain. Imagine only this file, we have designed the attention, basically the brain of this AI, and that means we are basically done with everything that we need to do. Basically, everything that else that we shall build later, it's nothing complex. We're not going to build anything complex. You're just now building the interfaces. The front end, the easy stuff. Because now we have the data, we prepared the data, we loaded the data, then we build the attention, basically the brain, and the building the brain is the hardest part. And because we are done, I think we can do what? We can end the session there. We can end the live there. So basically that's what next? Maybe in the next lesson, in the next live session, Yeah, the next session will be basically assembling everything into a complete model. Assembling, basically joining all these files. We have seen these files are not interacting either way. They are not, you are not referencing a certain file to come and play part in a certain file. No, we are not referencing that. Now we are going to combine all those into one. And then we build the interface of the, we build the interface, stop sharing. We build the interface of the system. Yeah, and that's it for today's session. I hope you guys learned something. I hope you learned something. In case you learned something, just say, hi, you learned something. Give me a like. Give me a thumbs up. In case you learned something, give me a thumbs up, guys. I'm waiting for your response. Did you learn something today? Yeah, it's complex. It sounded complex, but the more you do it, the more you get used to it, and the more it makes sense. So just keep learning, keep building. Make sure to subscribe so that in the next live you are here as we complete building a complete AI architecture. In case you're wondering, how do they build all these kind of systems? Yeah, that's how they do it. It's complex. That's why they get paid that's so much money, those engineers, to build these AI systems. That's the hassle that they go through. Anyway, thank you guys. Thank you for joining. I'm so happy you guys joined. I appreciate everyone who joined. See you in the next live on Wednesday, 6 p.m. East African time. Good day.